Hi everybody, this video is about solving polynomial and rational inequalities. Now before we get started, I want to let you in on the biggest hint when dealing with inequalities. You can see I've written it on the screen, and this goes for basically any type of inequality you ever want to solve, even in classes you haven't taken yet. If you ever want to solve an inequality other than just a very simple linear inequality, you make a Sine chart. That's what you do. And in this video I'm going to show you how to make a Sine chart. So we have a cubic polynomial, and we want to find when this is less than 0. Now, the first step in solving a polynomial inequality is to find the zeros. So that's what you need to do first. Now, this video would be way too long if we started from scratch to find the zeros. See some of my previous videos on finding the zeros of polynomials. So I cheated a little bit before pressing record, and I know the zeros of this polynomial are 2/3, 2, and 6. Which means in factored form, if 2/3 is a 0, well, we know x minus 2/3 is a factor. If x equals 2 is a 0, x minus 2 is a factor, and the same thing for x minus 6. Now, if you look carefully, what I've written is obviously not true. The leading coefficient of this polynomial is -3. But if you imagine multiplying this out, x times x times x, well, that's x cubed, not -3x cubed. It's really easy to fix this problem. If you found the zeros and weren't so worried about the factoring problem and you notice this little discrepancy, well, all you have to do is multiply by the coefficient that you want. So now the leading coefficient will be x times x times x times -3, so -3x cubed. And as long as you found the zeros properly, then this will be the correct factorization. So that's step number 1, find the zeros, which, as we know, is equivalent to factoring your polynomial. Well, now we're ready to make a Sine chart, whatever that is. So I'm going to draw what looks like a real number line. Now, I'm not drawing a graph. This is just a picture to help me organize my thoughts. And on this horizontal line, I'm going to plot my zeros in increasing order from left to right. And what I like to do is draw some little dotted lines to clearly separate this real number line into various subintervals. So we have 1, 2, 3, 4 subintervals. And what the question we're going to ask is this polynomial positive or negative on each of these subintervals? So let's do that now. And the way you do that is actually really simple. There's no work to do. All of the work goes on in your head. So I'm going to start with this far right subinterval. And you can pick any number that you want. So let's imagine we pick a number from this subinterval, and I'm going to pick, I don't know, 1,000. Normally in class I like to choose a really ridiculous number like 1,000,000 or 1,000,000,000, but I don't want to write that down. So in this far right subinterval, we're imagining the number 1,000, and I'm going to imagine plugging that in to this polynomial. So I'm going to plug it into all of the factors. Now, I'm not actually going to do any calculations. I just want to know if the value that I get is positive or negative. And that's why I chose a big number like 1,000. Well, 1,000 minus 6 is positive. 1,000 minus 2 is positive. 1,000 minus 2/3 is positive. So if you multiply these three factors together, you get a positive number, but then you're multiplying by -3. So the final value at x equals 1,000 is going to be a negative number. So we tested one number from this interval, and my claim is if you test one number from that interval and get a negative value, that means every number in that interval will give a negative value. And here's why that's true. To go from being negative to positive, you'd have to cross over an x-intercept. That's the way the graphs of polynomials work. But our Sine chart has all of the x-intercepts listed, so I can't go from being negative to positive anywhere in this far right subinterval. And that's it. That's what you do on all of the subintervals. So we go to this subinterval, I'm not going to draw the stick figure again. Maybe you choose the number 4. You don't have to write it down. I'm just doing that for emphasis. So when you plug in 4, 4 minus 6 is negative. 4 minus 2 is positive. 4 minus 2/3 is positive. And then you're multiplying by negative 3. So negative, positive, positive, negative. If you multiply all of those together, that means we're positive on this entire subinterval. Okay. And do the same thing on the next 2 subintervals. In the interest of time, I'm not going to bother you with plugging numbers into factors. It's a really simple operation to perform. Just realize the work is really going on in your head. There's not a whole lot to write down at this step other than the pluses or minuses in the Sine chart. Now, don't assume that every Sine chart is going to alternate like this one does. A lot of them do, but mean math teachers like to give you examples where the Sine chart does not alternate. Okay, now, don't forget to answer your question. We wanted to know, when is this polynomial less than 0? Well, that's what the Sine chart's for. Look for the minus signs. Less than 0 means negative. So we want to know, when is the polynomial negative? Well, it's negative from 2/3 to 2. And we're going to union that. That's the union symbol. If you haven't seen it before, that just means you're going to put 2 sets of numbers together. And we're also negative from 6 to infinity. And we're done. Just about notation, in case you haven't seen it before, if this problem said less than or equal to 0, the only thing that changes is the parentheses become square brackets, except not the one at infinity, because infinity is not a real number. So there we go. That's how you solve a polynomial inequality. In the next example, we're going to solve a rational inequality, but I'll go ahead and spoil the surprise. We're basically going to do exactly the same thing. So I'll clear the screen and bring up the next problem. All right, so we want to solve this rational inequality. Our first step is like before, where we're going to factor everything that we see. So in the numerator, that's a difference of squares. We have x minus 1, x plus 1. And in the denominator, we have, let's see, I hope I can factor this, x minus 6, x plus 2 seems to do the trick. And we want to know when this is less than or equal to 0. So the numbers that we have to worry about on our Sine chart in this example aren't just the zeros, but also the numbers that are not in our domain. So we have x equals 1, x equals negative 1, x equals 6, and x equals negative 2. So we'll start with negative 2, and then we'll go to negative 1, and we'll go to positive 1, and then we'll go to 6. And again, I like to separate my Sine chart really clearly. And just to prevent you from making a silly little mistake at the end of the problem, it's a good idea to distinguish the numbers from the numerator, so the positive 1 and the negative 1. So there we have zeros from the zeros that you get in the denominator, which are not zeros of the function. The x equals 6 and x equals negative 2 are not in the domain. So graphically, we would have asymptotes at those points. So we want to distinguish between the two. It's not that you have to write it down, but you'll see why I'm emphasizing it here in just a minute. All right, now we do the same thing as in the previous example. You choose a number from each interval. You imagine plugging it in, and then you ask yourself the positive versus negative question. So from the far right interval, again, I like to choose really silly numbers, maybe 10,000, because I'm not actually doing the calculations. I just want to know positive or negative. So 10,000 minus 1, positive. This one's positive, this one's positive, this one's positive. They're all positive, so that expression is positive on this entire interval. And then you go through and you just do that on every single interval. These small intervals, unfortunately, you have to pick some sort of a realistic number, so I'll choose 3. So if you plug in 3, 3 minus 1 is positive, 3 plus 1 is positive, 3 minus 6 is negative, 3 plus 2 is positive. So positive, 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 negative, combine all those, and you get a negative value. And again, guys, I'm not going to finish out the sine chart. It's just a matter of plugging in numbers. Let's see, this one is also going to be negative if you plug in a value, and this one's going to be positive, and this one's going to be positive. Now, it looks like, again, I have an example that alternates, but trust me, they don't all alternate, so you do want to test this. You can also use some facts about multiplicities of zeros, but I don't want to go into that in this video. All right, so now let's answer the question. We want to know when this expression is less than or equal to 0. So again, we're looking at the negatives, but since it says less than or equal to, well, we're equal to 0 at this point, and we're equal to 0 at this point. So how am I going to write the answer? All right, so we're negative from -2 to -1, and we're equal to 0 here. And then we pick back up at 1, we go to 6. But here's where you have to be careful, and here's why I distinguish between the zeros and the asymptotes. At x equals -2 and x equals +6, the value of the expression is not 0. It's undefined. The graph would have an asymptote. So we're going to put parentheses there. You don't include those points. So you have to pay attention to what type of number is in your sine chart in order to write your answer correctly. Anyway, that's how you solve polynomial and rational inequalities. See you next time.